Welcome to the Step Up to Vector Calculus workshop packet. So different than a topics packet, this workshop packet is going to go through a wide range of topics covered in vector calculus, and it's meant to be an intro. So this is a great thing to go over. This packet and video is a great thing to go over if you're preparing to take vector calculus and want to see a small sample of some topics you are likely to eventually encounter. Right? We're going to start with some basics of what is a vector, some vector notation, scaling vectors, magnitudes of vectors, creating unit vectors, vector projections, etc. A lot of big topics are going to be covered in here, just to give you a flavor of what's to come in your vector calculus class. So you may find that you go through this video now and you digest some of the information, which is great. And then you may find that later during your course, you want to come back and revisit some of the more complicated topics, for example, like rectangular regions in 2D or non-rectangular regions or vector projections. You might find you want to come back to this video and review these topics when your teacher actually starts to teach them so you can make those connections. Let's get started looking through our packet here, get our walkthrough going. So, what is a vector? That's where we want to start. A vector is a mathematical object with both magnitude and direction. So, magnitude means just the size or length of the vector. So, think of a vector as an arrow in space, or I consider it to be a line segment, a piece of a line that has direction pointing some certain direction and a magnitude, a length. Now, what that magnitude or length represents depends on the context of the problem, and you'll get into that as you start doing word problems that involve vectors. Vectors are used, again, in those word problems, physics, calculus, engineering, lots of different places vectors are used outside of just the world of math. So let's get started on example 1.1. We just have a set of directions here. The first bullet point says vector v. So notice there is a little arrow above v. That is one way to indicate that v is a vector. Another way to indicate that is by making v bold in text, or there's a little half arrow symbol, which I'll show later when I write, that also represents vector. So we see vector v starts at the origin and ends at a terminal point of 3, 4. We would refer to the origin as the tail point of the vector, and we would refer to the terminal point as the head of the vector. We might also refer to the origin or the first point, the tail, as the initial point of the vector. So you could have initial, tail, to mean the starting point, and then you could use terminal point or head to describe the ending point, just some terminology used. Awesome, so we have a description of vector v. Notice we have a description of vector w. We have where vector w starts and where it ends. And then in that third bullet point, we're just being asked to sketch v and w on the coordinate plane so that we can just visualize these vectors and see what a vector looks like. So let's get in there and start sketching. I'm going to zoom in a little bit on my coordinate plane. I know it's kind of a small graph going on here. I'm going to put my scale in. I'm going to scale by 1. So each of these tick marks will represent a 1. So I'll just put in there's a 5. Every tick mark represents a 1. So just getting in my scaling along my axes. All right, I know I wrote that in gray. It's kind of hard to read. I just didn't want to cloud the page. Now, how we create a vector is, let's start with vector v. I'm going to draw it in my purple marker here. Vector v starts at the origin, so I put down its tail point, and its terminal point is at the point 3, 4 on the grid. So go to 3, 4 on the grid. Awesome. Connect the dots from tail to head, and put the arrow pointing at the head or at the terminal point of the vector. So what I have drawn there is a representation of vector v. Let's do the same thing just to draw vector w so we can see it. Vector w, which I'll draw in blue. vector W starts at the point 1, -4. So on your graph, go over to 1, -4, throw a point down, and ends at its terminal point of -5, -2. So go to your graph, put that point down, and then connect from tail to head, and add your arrowhead. This right here in blue is vector W. Notice that little symbol I put above both W and V are that little half looking arrow. That's another way that we write vector, indicate that W is a vector or V is a vector. So you can put a full arrow above your V or W, or you could put this little half arrow. Both mean the same thing, just a different notation. So there we have it. We have visualized and sketched vector V and W. Those are what vectors look like. Kind of some notation on how we talk about them, the initial point versus the terminal point, or the tail point versus the head point. Now we actually want to discuss looking at vector addition here. Notice it says sketch vector V plus W. So that's something you're going to learn in your class. You're allowed to add vectors together. You can do other things with vectors too, but adding is one thing you do. I'm not going to go through what the algebra looks like on the addition. I just want to show you a visualization of vector addition. So to add vector V plus W, the first thing you do is you go in and sketch the first vector. Sketch vector V. So we did this before. I'm going to just scroll back up. I'm going to copy and paste down our vector V, just because I have it so nicely drawn above. But you can just recreate it on this graph. Get vector V drawn in, get your scale drawn in. Now, what you want to do from the terminal point of vector V, we want to draw vector W attached to the tail, attached to the head of vector V. So I'm going to scroll back up and I'm going to copy and paste vector W. But watch where I'm going to put it now on my picture. I am going to put vector W, so the tail of vector W is on the head of vector V. Let's get that in there nicely. Awesome. So there we go. Notice I'm going to draw on my highlighter. Notice I can take vector V, traverse that path, then traverse the path of vector W, one right after another. That's what vector addition looks like. One more thing to add in. So vector V plus vector W makes a new vector, and I'm going to show you which vector it is. So the new vector starts at the initial point of vector V and continues to the terminal point of what you get when you add the two vectors together. So this green vector right here represents vector V plus vector W. So if you wanted to get rid of all of the additional kind of riffraff, I think of it as get rid of the scratch work. That would be your final answer for what that new vector V plus W is. So there it is, just visualizing what vector addition means. It means traverse the V path, continue, traverse the W path, and then connect the dot from start to finish as if you were taking the shortcut, not traversing the paths. Now that we've visualized a few vectors and visualized that vector addition, let's look at vector notation on how we talk about vectors. So first, we want to look at a vector is in standard position when its tail, initial point, that's the tail, is at the origin. Then the vector components that we use describe the coordinates of its head position, its terminal point. This should still be a little confusing. We're going to explain what this means. But in general, we write vectors in standard position. So we need to learn how to do that. Moving down below, we are going to create vectors in standard position from 2 points. So this right here is just kind of a little formula that talks about how to create vectors if you're given 2 points. but I'm just going to teach you by example, but you can take some time to read through that formula if you want, or as a recap. So jump down to example 2.1. Let's just do one of these together. 2.1 says, express each vector described in standard position. So this is a skill you're going to get very good at and you want to get fast at. Part A says, a vector v starts from the origin, starts from 0, 0, and ends at its terminal point of 3, 4. This is vector v from the previous example. How do you create vector v using appropriate notation? So here's how we create vector v. Create vector v the following way. To create any vector, what you do is you take its terminal point, its head, minus its tail. So let's just make note of that. You take the head, or terminal point, if you prefer to call it that, and you subtract from it its tail, or its initial point, if you prefer to call it that. So you do head minus tail, and then we change to a bracket notation, an angular bracket notation. And as you subtract, remember, just you do the x, subtract the x. So 3 minus 0 is 3, comma, then you take the y minus the y. 4 minus 0 is 4. So that angular bracket notation is how we would talk about vector v. So we would say vector v in standard position is the vector 3, 4. I'm going to box this. And all that's saying is if the initial point is on the origin, then the head will lie at the point 3, 4. Now this is kind of a basic example because the initial point is already on the origin naturally. Let's take a look at what happens if we don't start with our initial point on the origin, as in vector w. So we know the initial point of vector w, and we know the terminal point of vector w. So to create vector w, w will equal, we take the terminal point, subtract from it the initial point, and we will create the component form. That's what we're going to be creating over here. This is called the component form of the vector, and that's why we use the angular bracket notation. And don't forget, you're going to go negative 5 minus 1. Negative 5 minus 1 is negative 6, comma. Then you're going to go negative 2 minus negative 4. That becomes 2. So what this tells us about vector w, I want to sketch this for us. This is the same vector w that we visualized in example 1. So notice in example 1, the first example, when we sketched vector w, it looked something like this. I'm not putting in the scale, I'm just showing you roughly. When we originally sketched vector w, it looks something like the following little sketch. But now if you were to sketch vector w in standard position, this would look like, so standard position always starts the tail at the origin, and then the coordinates here, negative 6, 2, are the terminal point of the vector. So you would go over to where x is negative 6, up to where y is 2. And this would be vector w in standard position. So notice all we did essentially was picked up vector w and moved it so its butt was on the origin. Again, right? You just copy and pasted vector w and moved it so its butt was located at the origin, or its initial point, or tail, whatever you want to refer to that as. This is what it means to have a vector in standard position. And this notation right here is how we write a vector in standard position. So this negative 6, think about it, it's the x coordinate. This 2 is the y coordinate of the final resting place of the head of vector w if the butt is at the origin. Let's just do one more example, but notice example C is now in 3 dimensions. And I'm going to show some other notation that can be used. So a vector u, we're looking at a vector called u, starts at a certain point and ends at a different point labeled P and Q. Let's create this vector in standard position. U, vector u, so I put the little u and the vector sign above it. Vector u can also be written as the vector that goes from P to Q, point P to point Q. Both of those say the same thing. So this part right here is calling the vector by name, vector u. This right here is describing the initial point. Oh, I wanted to write that in my pen. The initial point comes first, and the terminal point comes second. That's another way to just describe vectors in some notation. But the calculation is still the same. No matter which way you describe that vector, whether you call it by its name or you call it by its points, we calculate it by doing the head minus the tail, or the terminal point. The terminal point, -6, -3, 7, minus the initial, and then you just do your subtraction component-wise. So vector u will equal, you go to angle brackets, and then recall you just subtract -6, or excuse me, you take -6, subtract -1. This makes -5. Move over to the y's, -3 minus 4. And then do your final z component. So there's an x, y, and z component. That's what you found. This is the x, this is the y, and this is the z component of vector u in standard position. So that is how you would create vector u from the 2 points given to you there. So I've used this word component form a few times now. Let's go down and check out what that means. So vectors can be written in component form. So just to point out, in 2D, component form is just the xy, which we've worked on. Or in 3D, component form is the xyz, which we just did an example of. So that's one way to think about vectors. That's component form. Or in IJK notation. Before we get into that, though, we need to learn what IJK notation is. So component form is outlined in the first box there. Hopefully that makes sense on the way we wrote it. Now, IJK notation involves these definitions of vector I, vector j, and vector k. Vector I, j, and k are specific vectors. And notice how they're defined. Their definition is listed right there. Vector I is the vector where x is 1, y is 0, z is 0. Notice vector j has y as 1, with the other components are 0, and then vector k has z as 1, with the other components 0. So when someone talks about IJK, they're referring specifically to this set of definitions for IJK if you're in 3D. Take a note down below if you're in 2D. Then you don't have that third component. In 2D, you don't have a z value, so you only have vectors I and j. We wouldn't talk about vector k, and then notice I and j got modified to be in 2D, just having 2 components. So let's just take a look at how do you convert between forms. So example 2.2 gives us vector A in component form, and it asks us to convert this to IJK notation. This is not a terrible task. Once you get used to it, you should get good at going back and forth between forms fairly regularly. To take vector A and put it into IJ notation, you just take your first component, your x component, 2, multiply it by the I, plus take your next component, the y, and multiply it by the j vector. Now, normally we wouldn't write a plus minus. We would just write A is equal to 2I minus 3j. So this would be vector A written in IJK. Well, it's not going to be a K because it's 2D, so an IJ notation. Let's just take a look at y. Let's just increase that understanding. Well, let's look at what this is saying. Vector A, if we write it in this IJ notation, is 2 times vector I. Well, vector I is defined to be the following, minus 3 times vector j, which is defined to be the following. And then let's do some multiplication here. We are allowed to, and we'll actually look at this in one of the next sections, but one thing you're allowed to do is multiply a vector by a scalar. So we can multiply that 2 through, minus, multiply that 3 through, and then combine component-wise, right? Meaning you take 2 minus 0, that'll give you your first value, and then take 0 minus 3, that'll give you your second value. So hopefully that y could show you that, these in fact do say the same thing based off of these definitions of what I and j are. So let's do example 2.3. But now it's the opposite. We are converting vector B, convert vector B to component form. So we can do this without going through all of that y. We can just say, okay, looking at vector B, going to component form, the value multiplying the I will be the x component. The value multiplying the j will be the y component. And then the value multiplying the k will be the z component. So there it is. There is component form versus up above, you see the IJK notation. So hopefully it becomes fairly fundamental to transfer back and forth between forms depending on your needs. So keep going. Let's talk more about vectors. So we saw how we talk about vectors two ways, in this component form and in this IJK or IJ form, depending if you're 2D or 3D. Now we want to go focus on another way we talk about vectors, and it is actually by using a completely new coordinate system. So polar coordinates are coming back to us. At some point when you took a trig or a pre-calculus class, you should have studied a little bit about polar coordinates. In case you haven't, I'll give you a reminder here. But polar coordinates, so let's read here. Vectors in 2D can be described in polar form or polar coordinates, and that's where you describe the vector by an r, a radius or a magnitude, and a theta, which is a direction. And remember, we measure theta from the positive x-axis. That's the standard position for measuring an angle. So polar form involves an r and a theta. Cartesian form is xy form. That's the form you're kind of used to. So Cartesian form is xy, polar is r and theta. And then you will learn different coordinate systems for 3D vectors. There's actually a few coordinate systems we use for 3D. That gets more intense, and we're not going to cover that in this packet. But if you do get to that in your class and you want to see me go over the coordinate systems for 3D vectors, I can definitely get us a video for that. A quick recap on some of the conversion factors on how you convert between polar and Cartesian. I didn't put all the conversion factors up here. Just a reminder though on how to calculate x and y and going from Cartesian to polar. Again, this is something you should have seen in a trig class or a pre-calculus class, trigonometry at some point. And we'll go through some examples to hopefully refresh your mind about it. So example 2.4, consider vector g with a given magnitude. So this magnitude is our r in polar form, and the direction, the theta, in polar form. Now, remind yourself, if you have a hard time thinking in terms of radians, pi over 3 is 60 degrees. So if that just helps you visualize better, pi over 3 is 60 degrees. And we are being asked, the question at hand is convert to Cartesian. So our goal is to find the xy form of this vector. So the first thing I always do whenever I'm converting is sketch the vector. Vector g. Sketch vector g. It doesn't have to be a perfect sketch, just on your paper so you can visualize where vector g is and what you're finding. Get in there. Remember, vector g starts in standard position, so we put its tail at the origin, and then we need to follow the set of directions. We need to be 60 degrees off the positive x-axis with length 5. So vector g would be approximately here. The length of this vector is 5, and the angle off the positive x-axis is pi over 3. So there's a quick sketch of vector g. And now keep in mind what we're trying to find is we're actually after the x-coordinate and the y-coordinate of where this final resting place, where the head of vector g lands. So that's what we're after. And this just involves some right triangle trigonometry. You could use the conversion factors I gave you, or if your trig is strong, you could make a triangle and then go about finding the missing sides. Let's convert to x, y. I am going to use the conversion factors given to us in the text above. One of the conversion factors tells me that x is equal to r cosine theta. Again, that formula just comes from some right triangle trigonometry. Now, x will equal, I know my r is 5. 5 is the length of the vector, times the cosine of the angle, pi over 3. You may have to pull that cosine of pi over 3 off a unit circle, or if you have it memorized, you'll know the cosine of pi over 3 is 1/2. Therefore, my x component can be written as 5/2. Let's do the same thing. Let's find the y-coordinate. Again, the formula for the y-coordinate is y equals r sine theta, found using right triangle trigonometry. And then we plug in the pieces we know. We know the radius is 5. We know the angle is pi over 3. Sine of pi over 3 is a number that exists on your unit circle, and it is the square root of 3 over 2. So my y component is 5 square roots of 3 over 2. Awesome. So when I want to write vector g, I'm going to write it in the bottom left here. Vector g in component form is x, comma, y. There I have it down here. Here is vector g. I converted from polar to Cartesian. Now that we've gone from polar to Cartesian, let's go from Cartesian to polar just to practice the other way. So part B, that's what part B is having us do here. Part B says consider vector f in standard position, and we are given vector f. So the way this is written tells me that that is the x and y. And our goal is to convert to polar form. So our goal here is to find r and theta. So first thing I do again is sketch. I'm going to sketch vector F. This is important for a few reasons, and we'll see a little bit more when I get into the calculating why the sketch is so helpful. But just trust me until we get there. So sketch vector F. Look over at vector F. Its terminal point is -3, -3. So remember, it's in standard position. So its butt is at the origin. And then its head is located at -3 on the x and -3 on the y. So its head is just like so. So there is vector F sketched for us. And remember, now we're on a hunt for r, which is the magnitude of this vector. And we're on a hunt for theta, which is the angle off the positive x-axis. Those are the components we're trying to find. You could use some right triangle trigonometry to find it, or you could use the conversion factors that were provided. So let's start our converting. We are trying to convert the vector -3, -3 over to r theta. How do we go about doing this? Well, one is thinking about your conversion factor for r, but this is nothing more than a Pythagorean theorem. If you were to draw a right triangle, trying to just highlight that in pink, you could use the Pythagorean theorem to find the r value, the magnitude of this vector. So the conversion factor above lists r equals the square root of x squared plus y squared. But just think about that. All that is, again, is a Pythagorean theorem to find the length, the hypotenuse of that triangle. So in our context, r will equal the square root of x squared. Make sure you put it in parentheses because that negative is also getting squared, plus y squared. Cleaning up, this gives me r equals 9 plus 9 under the square root, which then gives me r equals square root of 18. If you want to take that into simplest radical form, you can. I'm just going to leave it right now as the square root of 18. So I have my r value. Now I need to go about my theta value. You'll see in the conversion factors listed, the theta reference angle can be found the following way. So the theta reference angle can be found by taking the inverse tangent or arctangent, depending on which notation you use, of y over x, again found with some right triangle trig. So this tells me that my reference theta, and I'm going to talk about what that reference means here in a minute, can be found by taking the inverse tangent of the y divided by the x, -3 divided by -3. So you would either need to know this value or take that to a calculator and find the inverse tangent. So whether you know that from the unit circle or find it from a calculator is fine. And what you find out is, and I'm just going to write it right here to give us some more room, the reference angle gives you pi over 4, or if you prefer in degrees, 45 degrees. This is not the angle we are looking for. This is the reference angle. I'm going to go to our triangle, and in my little green highlighter, I'm going to show us what angle this formula found for us. So zooming in on our triangle, real big here. Let me delete the other thing in the way. What we found for us was the reference angle. The angle between our vector and the positive x-axis is 45 degrees. This little tiny angle in here is 45 degrees is what we found. That is not what we're looking for though. What we're looking for is the entire angle. So just seeing, we have the little angle is 45 degrees, and we would need to add to that the 180 full line to get there. I'm going to write that in math. I know I just explained it in words, but zoom back out. So what do we need to find our theta? Just going to do this off to this side since we're running out of room. Our theta is going to equal 180 degrees plus the 45-degree reference angle. So our theta is going to equal 225 degrees, or if you prefer in radians, this would be 5 pi over 4. To summarize, the F vector in polar is the radius, comma, or some texts or books use a colon, the angle. So at the end of the day, here we did it. We took our XY component form in Cartesian and we converted it to our vector polar form. Next topic, talking about scaling a vector. I kind of mentioned this before, but let's get into the actual definition of what scaling a vector means. So, scaling a vector means multiplying a vector by a scalar, which is just a number. So like a constant, 10, -4, 12. We can multiply vectors by scalars. When you multiply a vector by a scalar, it scales the vector. That's why it says scaling a vector means multiplying it by a scalar, which changes the magnitude, but not the direction. However, a small exception to that. So multiplying by a scalar changes the magnitude, not the direction, unless the scalar is negative. If you multiply by a negative scalar, that reverses the direction of the vector. And we'll take a look at what that means here. A little formula up here on how to multiply by a scalar, but again, if I teach you by example, usually that's just a little bit easier way to learn than reading math definitions. So example 3.1, let's look at part A. Vector v is defined for us in standard position. We are asked to find 3v, 3 times v. So 3 times vector v can also be written as 3 times vector v, and can be calculated by just distributing your scalar through. To summarize, 3v is equal to the vector 3, 6. So I will say 3v is pointing in the same direction as v, but there's a but here, and I'm just going to move things over to get the but in. What's different about it? So vector 3v, which we found, is pointing in the same direction as vector v, but is 3 times longer, or has 3 times the magnitude, if you want to use that fancy term, the length, 3 times longer. Let's just try it again on vector w. Notice vector w is given to us in IJK notation, and then we are asked to find -1/2 of vector w. That's okay, we can still do this in IJK notation. -1/2 of vector w can be found by taking 1/2 times the vector in IJK notation. So all I do again is I just distribute that -1/2 all the way through that vector, and I wind up with -3 halves I plus 1/2 j. Remember that negative is distributing through also, minus 4k. So again, all I did was distributed that -1/2 to every term. This would be an appropriate way to write -1/2 of vector w. using component form. Excuse me, not component form, using IJK notation. Got ahead of myself. Now I am going to do it in component form. So I'm going to do the same problem twice just to show you. If I wanted to do this in component form, so let me write that over here, component form. Maybe for whatever reason I just don't like the IJK notation. I want to convert to component form. So the first thing I would do is I would rewrite vector W in component form, right? So go over and pick off the coefficients in front of I, J, and K. So this would be I goes first, -1, 8. So there is the vector in component form. And then let's say I wanted to do the scalar -1/2 times W in this form, -1/2 times W. This would result in, just filling in the nuts and bolts. Remember, just take this -1/2 and distribute it through. This would result in -3 halves, 1/2, and -4. So you'll see at the end of the day, if I box this answer here, I'm going to grab my little laser pointer now, you'll see here that the final answer in component form is the same thing as the final answer in IJK form. Totally up to which you prefer and what you like to do. We've done a few scaling examples. Let's just look at a couple of conceptual questions about scaling just so we understand it. So this question C is not referring to any specific vectors. It's just talking about in general. In general, how are vector u and 2u related to each other? What do they have in common? And what is different? So let's just create a little sentence here. The vector 2u points in the same direction as vector u. But what's different about it? Let's add that. So vector 2u points in the same direction as u, but the vector 2u is twice as long, or twice the magnitude, is twice as long as vector u. That's the only thing that changed when you multiplied by the scalar 2. It changes the magnitude. Let's just double check part D now just to make sure. So back to in general. In general, how are vector v and -v related? So the vector -v. Now notice quickly, I'm going to write it underneath here. This is saying -1 times vector v. So the scalar you're multiplying by is actually -1. I'm going to erase that just so it's not in the way of our sentence. But when you process -v, you want to think of it as -1 times vector v. So the vector -v or -1v points in the opposite direction of vector v. The reason it points in the opposite direction is because the negative sign points it in the opposite direction. But negative vector v has the same length as vector v. Since the scalar is -1. So the one part of the scalar keeps the same length. The negative part of the scalar changes directions. Just to show you in general, just a quick little sketch in general, I'm just going to make up a random vector v so you can visualize this. If vector v looks like so. Again, this is just a random vector I made up in my mind. What would vector negative v look like? So it should keep the same length, but just go the opposite direction. So roughly, this would be an example of v and negative v. Same length, same slope to it, but just going the other direction. So now that we've talked about scaling vectors, we need to look down at what the magnitude of a vector is and how to find it. We've used this word already a few times, so let's just define it a little more clearly. The magnitude of a vector is its length. So it's how long the vector is. We denote it by using these absolute value signs. So this right here that I have circled is read out loud as the magnitude of vector v. We don't call it the absolute value of v, even though we use the absolute value signs. We would call that the magnitude of vector v. And you have a formula for 3D and a formula for 2D to find the magnitude of a vector. Just remember, this is a Pythagorean theorem. It's just glorified for 3D, right? There's an extra component, or it's just the Pythagorean theorem essentially in 2D. Let's do our example. Find the magnitude of vector u. So the magnitude of vector u can be found by taking the square root of the x component squared plus the y component squared plus the z component squared. Clean this up, gives me 1 plus 4 plus 4. And this should come out to a nice number. So what did we find? We found that the magnitude of vector u is 3. I'm going to write that. This is the magnitude or length of vector u. So this didn't find what direction this vector is pointing. We didn't get into the direction. We just literally found the length of that vector. So if you walked the path of that vector, you would walk 3 units, whatever those units are. Let's just do another. Part B, compute the magnitude of vector w. Notice there's only 2 components given to us here. So compute the magnitude of vector w using appropriate notation. We would say the magnitude of vector w is equal to, and then this formula again comes from just the right triangle trigonometry of finding the radius or finding the length of a vector if you created a triangle. And that's where this formula comes from. Right, I took the x component, squared it. I took the y component, squared it, added them together. Be very mindful, these parentheses are important because that negative is also getting squared. So now when I just try to clean this up, I get 25 plus 144. And this has a nice value of 13. So the magnitude of vector w, the length of vector w is 13. And the units, 13 what, depends on the context of the problem. Sometimes we use magnitude to represent length, like the trail you're walking. Sometimes vectors represent a speed or a rate. Maybe a plane is traveling at a certain speed and we use the vector to describe its speed. So 13 could represent the speed of a plane traveling. That could be 13 miles per hour. That could be a force. That could be 13 newtons. It all depends on the context of the problem, but the length will be 13. And then again, the units will depend on context if you were doing this in a word problem. So we've calculated the magnitude now of a few vectors, which leads us naturally into a new concept of a unit vector. So we need to figure out what a unit vector is and how to create one. So a unit vector, sometimes denoted with a hat. I'll explain what this means in some notation. Sometimes denoted with a hat. v hat, notice there's a little it's a tiny little hat up there, has a magnitude of 1. So all unit vectors, anything that's a unit vector has a magnitude of 1. That's what unit vector means. Unit vector referring to one unit. So a unit vector has a magnitude of 1, and it points in the same direction as the original vector. Here's a formula on how to find a unit vector for a certain vector, but again, I'm going to walk you through that example. So we have a vector x here, and we are asked to find its unit vector. That means the first thing we need to do is find the magnitude of vector x. So the steps to create a unit vector. So creating a unit vector. Specifically, we're creating a unit vector for x, right? For this vector x. So step 1 is find the magnitude of x. Let's find the length of x. We do this by taking each component squared, right? Pythagorean theorem to find the magnitude. Okay, so this is the length right here. This number, square root of 2, is the length of vector x. So now that we know the length of x, the next step is to actually create this unit vector part. You might call this x hat, depending on the book, text, or whoever teaches you. But if you do use this notation, x hat represents the unit vector of vector x. And you find this by scaling the vector down. So let's think for a minute of what we're doing before we actually do it. Vector x has a certain length, and maybe the length is smaller than 1 or greater than 1. But the goal at the end of the day is to take this vector and either shrink it to have length 1 or grow it to have length 1, right? So it's just like a scale model of something. You have a model of a certain length and you just want to scale it so its length is 1. The way you do that is by taking the vector itself and dividing by its magnitude, right? Like shrink it down to size, essentially, or grow it up to size. What this looks like mathematically is you take your vector x and you divide each of its components by the magnitude we just found. Let's summarize what we just found. So this vector, I'm going to change colors here. This vector, x hat here, right here, the one we just created, points in the same direction of the original vector, in the same direction of x, but has length 1. Right? All unit vectors have length 1. That's the definition of a unit vector, and we found it. Let's just do it again, right? Practice, practice, practice. So compute w hat, which is the unit vector for the w vector. So let's create this again, following our process. First process is to find the magnitude of vector w. Pythagorean theorem for 3D. Clean up, be careful of your signs. So the length of vector w is the square root of 8. Again, you could go to simplest radical form. I'm not going to. And then follow your process to find w hat. Remember, this is found by taking the original w and dividing everything by its magnitude. So what I do is I take my components. I take the first component, divide by its magnitude, the second component, divide by its magnitude, and the third component. Oh, there we go. My brain doesn't want to keep up with my pen, but I think I got it. There we go. So there it is here. This right here, this vector represents W hat. That vector that I have boxed points in the same direction as vector W, but has length of 1. If you're not convinced by that, double check this. Go through the process to find the magnitude of this new vector, and you should find that it has length 1. That's the definition of a unit vector. If it doesn't have length 1, then we messed up. Then we didn't actually create a unit vector. I do want to show you another way you might see this written. Sometimes people actually keep the magnitude out in front as a scalar. So for example, this, instead of dividing by this square root of 8, some people will write this as 1 over the square root of 8 times just that original vector. This says the same thing. If you notice, this algebraically is the same. That is 2 ways to write the same thing, a unit vector for vector W. Now a quick crash course in part C, we're going to look at why might you want to find a unit vector. There's lots of reasons. Actually, we're just going to look at one since this is just a little sampler. So part C says, find a vector in the same direction as vector B, but has a magnitude of 9. So we want to take vector B. We want to create a vector that's in the same length of vector B, but we want it to have length 9. One of the easiest ways to go about doing this, but I want to point out it's not the only way to do this. There are lots of ways to answer this question, but one of the most common ways is to first create the unit vector for vector B. B hat is a unit vector for vector B. So that is step 1 of what we are going to do. So creating that unit vector, first thing you do is you find the magnitude of the original vector B. Right, go grab your x component, square it, plus your y component, square it, plus the z component squared. Clean that up. This gives me the square root of 4 plus 11 plus 1. That ends up being the square root of 16, which is just 4. All right, what we found out is vector B has length 4, right? The original vector, vector B, has length 4. Our goal is to scale that vector so it has length of 9 instead of 4. So we want to make some modifications. We have right now a vector of length 4. We want to scale it up to have length 9. One of the easiest ways to do that, in my opinion, is now go to that unit vector. Give me that unit vector. So find B hat, which means we take the original B vector, right, and divide each component by its magnitude. So recap, this is the unit vector. So this vector right here has length of 1, but is in the same direction, squeeze in that word, as the original B. Why did we do that? Because now we have a vector of length 1, and we can easily scale that to have any length we want. If we want it to have length 100, we multiply by 100. If we want it to have length 1,000,000, we multiply by 1,000,000. We want length 9, so we multiply by 9. So 9 times the unit vector will give us what we want. This will be 9 times, I'm going to reduce that fraction. Negative 2 over 4 can be reduced to negative 1/2. So this is actually considered potentially a final answer. This vector that I am boxing right here is in the same direction as vector B, but it has length 9. You can also, just a heads up, you can distribute that 9 in. So this could be written as negative 9/2. 9 square root's 11 over 4. All I'm doing is multiplying that 9 in. Both of those say the same thing. So this vector, at the end of the day, let's just label it. This vector has same direction as B with magnitude or length 9. And again, if you're not convinced, take this vector and find its magnitude. Go through the process to find its magnitude using your magnitude formula, and you will find that it has length 9. Another thing to do also to help your understanding is find a 3D grapher online, graph this vector, also graph the original vector. Notice they will point in the same direction, but one of them will have length 9 and one of them will have length 4. Moving on to a new concept. So this kind of gives a little flavor of unit vectors and where they might be used. We're going to jump into the concept of vector projections. A brand new topic now. Let's take a look at vector projections. So in general, when we talk about vector projections, we're normally talking about an orthogonal projection. An orthogonal projection is a perpendicular projection. And it's very important that we get the notation right so we understand it. So reading along here, the orthogonal projection of V onto U, it makes a difference on how we say this. So vector V onto U is different than U onto V. Keep that in mind as we sort this out. The orthogonal projection of vector V onto vector U is the shadow, it's the way I think of it, that V casts onto vector U perpendicular to the line through U. Kind of hard to say, and that's why I'm going to teach this to you in pictures. Just a heads up on more notation. The orthogonal projection of vector V onto U is written the following way. It's the projection of V written up top and U written as the subscript. This actually creates a whole new vector. So that projection notation is representing a new vector that forms when you project V onto U. Now, in your vector calculus class, you're going to learn formulas on how to find these vectors. Today, I'm not going to teach you those formulas. I am just going to teach you what it looks like visually to project a vector onto another vector so you can have a little bit better understanding of it when it comes time to find those formulas. So the first example, 6.1 here, defines vectors U and V for us, asks us to sketch U, V, and then the projection of V onto U. This is the new skill. So first thing, let's just go about sketching U and V onto our graphs. So I'm going to sketch vector U in my purple here. So vector U is the vector 2, 0. I'm going to blow up my scaling a little bit on my graph just to make it easier for us to see what's going on. So I'm going to call that first tick mark 1, and I'm going to call the second tick mark 2. I'm also going to scale my y-axis the same way. So there's 1, 2, 3. I won't put in all the numbers, but just that's how I'm going to choose to do my scaling. And let's graph in purple vector U. Vector U starts, remember it's in standard position. So it starts at the origin and its head ends at the point 2, 0. So it's actually laying on the x-axis. There is vector U. Let's get in there now with a different color. I'm going to pick my blue and I'm going to sketch vector V. Vector V starts at the origin, it's in standard position, and ends at 1, 3. So let's get that in there. There is vector V. All right, now the new skill is sketching this projection. This is the projection of V onto U. So U is written as the little subscript. We are projecting V's shadow onto U. So the first thing you want to do is think of vector u as like the floor. We're projecting onto the floor. We go and we find the head of vector v. So find the head of vector v and sketch until you reach vector u at a right angle. So you take the head of vector v and you sketch till you meet vector u at a right angle. The shadow that you would create, I'm now going to write in my green marker, the shadow that you would create is that green vector right there. So that green vector that I drew right there is the projection of v onto u. And because I happen to pick a little bit easier of an example, I can actually see what that vector is. The projection of v onto u is the vector 1, 0 in this case. Again, there's a formula to actually find that algebraically, but I happen to give us an easier example so that we didn't need a formula to find that vector. We could just find it by visualization. But in your class, you will actually learn a formula on how to calculate that vector projection. Let's do things a little differently now. In our next example, let's visualize a different projection. Same vectors, u and v, but now we're being asked to find the projection of u onto v. So let's just clarify. This is the projection of u onto v. This changes everything. First thing though is let's get our vectors u and v sketched. And let me check my scaling. I'm going to scroll for a minute just to see how I scaled before, and I want to keep that same scaling. Perfect. So let's go put that same scaling down. I'm actually just going to copy and paste this and then adjust it very quickly here. So let's get this, since this was drawn so nice, let's get that same scaling in, and I'm going to erase some of the marks we don't want just to get our structure set up here. All right, so as you're creating your picture, the only thing I have on there so far is vectors u and v. That's what you want. So I removed everything else. I wanted to sketch vectors u and v. I have done that. Now, we are projecting vector u onto vector v. So in this instance, you need to think of vector v as the floor. So that's why I kind of extended in my mind. I think vector v is my floor here. Oh, that didn't go straight. Vector v is the floor. So I need to go to vector u. I find the head of vector u. And now I need to sketch where vector u meets vector v at a right angle. This is just an approximation, but if I had to sketch approximately, vector u would meet vector v at a right angle approximately according to this line, right? My goal is to have a right angle right there. So this is just a sketch, it's an approximation, but what that finds for me is the projection vector. This little piece right here is my projection of u onto v. So that little piece right there is the projection, the shadow of u onto vector v. Now, because that's not located at a nice point, I can't tell you exactly what that vector is. I would need a formula to calculate the exact location of that vector. And again, you're going to get that formula in your class once you get into this material. But at least now you have a visualization of what exactly you're finding when you are doing projections. The last main topic here we have is sketching regions. We do two different types of sketching. First, we learn how to sketch rectangular regions, and then we'll talk about sketching a non-rectangular region. That'll make more sense here once you see these examples. Where you're going to use this skill is when you get to the point in vector calculus where you're taking double integrals. So you're going to actually do double integration. That might be a new scary term for you. So think about in your integral calculus class, you did just single integration. You did one integral. We're actually going to learn in vector calculus how to do two integrals at the same time, what it represents, what it means. But essentially, it's taking one integral and then from there, taking another integral. We just call it double integration. It's just doing the same process twice. Now, a skill involved in double integration is sketching and slicing certain regions. So sketching and slicing should be a familiar concept to you from your integral calculus course. Remember when you found volumes and areas, you had to sketch and slice shapes? That's what we're learning how to do again, just in a little bit different context. So in vector calculus, we often define 2D regions to integrate over. It's important that we're able to sketch these regions and describe them mathematically. First example, we just want to practice the sketching. Sketch and shade the region where x is between 0 and 2 and y is between 1 and 3. So just writing this in a different way, just writing this piece in a different way tells me x is going to go from x equals 0 to x equals 2. Those are the endpoints of the boundary. And then y is going to go from y equals 1 to y equals 3. Let's sketch all of those pieces. I'm going to start with x equals 0. X equals 0 is a vertical line located on the y-axis. X equals 2. Well, let me put my scale in. I didn't get my scaling in. Let's just call this 1. Let's call this 2. So on the other axis, this will be 1. Awesome. All right, let's keep sketching. So I sketched x equals 0. Now I need to sketch x equals 2. That's a vertical line at 2. So there I've sketched my x boundaries. Now let's go down and sketch the y boundaries. Y equals 1 is a horizontal line at 1, and y equals 3 is a horizontal line at 3. Sketch and shade the region bounded between all of those boundaries. That is this region in here. Now, it's often that you're going to end up doing something with this region later on in your vector calculus class. So sometimes once I've created my sketched region, I go in and I just kind of delete or get rid of, erase the extra pieces that I don't need. Like these guidelines are just kind of clouding my image. So I might go through and erase those extra guidelines once I have that region nicely sketched. This is just good cleanup practice to help you with your visualization. Obviously easier to do with a tablet than it is on pen and paper. But there it is. We have sketched and shaded the region described by the given inequalities. As you can see, that's why we call this a rectangular region. The shape made for us was a rectangle. Let's practice one more. It doesn't get too much more difficult than that to sketch a rectangular region. Let's just make sure we can do it one more time. So sketch and shade the rectangular region bounded by x is going from 1 to 4. So this means we're going to go x equals 1 to x equals 4, those two vertical lines. And then notice y has a set of directions as well. We're going to go y equals -1 to y equals 2. We're going to create those boundaries and we're going to shade. Let's put in my scaling first before I start graphing. Scale however you're most comfortable. Oh, I'll just go up by 2. So let's call that 1. Let's call that 2. And then let me mark my other axes. That'll be 1, 2, 3, and 4. There we go. All right. So I'm going to sketch my x's in pink again. X goes from 1. That's a vertical line at x equals 1. So just putting in that vertical line. X goes from 1 to 4. And again, this technically is a line that continues forever, but since I know I'm sketching some region, I'm just kind of getting in like the framework here. And then y needs to go from -1, so sketch where y equals -1 based on my scaling. That would be right down here, y equals -1, up until y equals 2. And hopefully you can see the region that's bounded. it's the region in that rectangle right there. And like I said, if I'm doing something, I often go through and delete some of the additional parts of the picture just to make it more clear on the next steps. Like, what am I going to do with this region? And visualize what's going on. But there it is. I have sketched and shaded that rectangular region. Now, what happens when the regions are a little more complicated and they're not rectangular? That's going to be our last set of examples. We're going to learn how to think about a non-rectangular region, specifically how to think about slicing it as well. And then that'll wrap up kind of our topics in this workshop. So non-rectangular regions have bounds that depend on other variables or functions or equations. This skill, again, is going to be a little more robust than the previous one, and it's going to prepare you for double and triple integrals. I didn't mention triple integration, but that is something that's going to come your way. You're going to learn what it means to take a double and a triple integral eventually in your Vector Calc course. So let's jump in. Example 8.1. Sketch the region R bounded by, now we're given a more complicated set of directions. So we need to go in and sketch and shade the region that's being discussed. So let me get in and scale my picture. Before I start my sketching, I'm going to go in and just mark, let's call that 5. Just every tick box, every box in here is going to be a unit of 1. And I'm going to just get this sketch in here. So first thing I'm going to graph is the line y equals 1/3 x. If you need to review some graphing skills, might be important for this class, but let's get that graphed in there. Y equals 1/3 x starts at the origin. Its slope is 1/3, so it goes up 1/3 to get to the next point, up 1/3 to get to the next point, and connect the dots. I'm going to try to make this look as nice as I can. Oh, there we go. That's not a bad looking line. I'm fairly happy with that. So this is the line y equals 1/3 x, just labeling it so we don't forget for later. So I have sketched the first set of directions. Now I'm going to grab a different color. I'm going to go sketch y equals 2. Y equals 2 is a horizontal line at 2. So y equals 2 should look, there's y equals 2. And then x equals 0. X equals 0 is the y-axis. So that's the line x equals 0. It's the y-axis. And we want to sketch and shade the region bounded by all 3 of those graphs. So the region trapped between those 3 graphs is this shaded part of this triangle. So we are focused on just the shaded part of this triangle. So part 1 here kind of said sketch and shade the region R. So this shaded part is what we would refer to as R, bounded by those curves. Now, part A has a new spin for us. If the region R is sliced vertically, describe the region using inequalities. All right, so slicing region R vertically means we are going to go into region R and slice vertically. And what I do is I think of all of those slices, actually think of those slices as a person. So the head is in the positive direction, the feet are below you. And since it's a vertical component, since we are slicing vertically, the first thing we do is, I think, describe y. These are just my terminology, my words I use to remind myself as I'm doing this. So slicing vertically means you first describe y and then you restrict x. And I'm going to explain what that means. So first thing I'm going to do is describe y, since it's a vertical slice. Where is y trapped? Over here, I need to think about, what do the feet touch? If you think of each of those slices as a person, think of the floor. What is the floor? Well, let's go over with my laser pointer. The floor, if you think of a slice, the floor is this slanted line. That slanted line is where everybody's feet touch, right? That slanted line is the floor. And since we're looking at it in y perspective, we need this value over here to be a y equals quantity. Well, we do know the floor of this is y equals 1/3 x. So y is bounded below by 1/3 x. Now, similarly, since we're trying to describe y, we need a y equals on this side of the inequality. Where is the ceiling? Think about your slices. Who does everybody's head touch? Well, everybody's head touches that horizontal line, which has the equation y equals 2. It's already in y equals format. So y is bounded by the ceiling and the floor. I'm going to write in those words. If that helps you think about it, we have the floor in y equals format, and we have the ceiling in y equals format. That is how you describe y. And now to restrict x just means we are looking for the smallest x value. If you think about this shape over here, the shaded region, go in there. I'm going to take a bright pink highlighter. What is the smallest x all the way up to the largest x that keeps you in your shaded shape? The smallest x is 0. And you can see on the picture the largest x is 6 because these lines actually intersect. The shading stops here at that value of 6. So to describe this region in vertical slicing, we would describe it the following way. This would be the way to think about that vertical set of slices. Now, one more example on the same problem, but a little twist. If the region R is sliced horizontally, describe the region using inequalities. So horizontal slices mean first describe x. That's the way my brain thinks. And then restrict y. So we need to go back up to our picture. I'm going to do some erasing here, or if you prefer to resketch the picture below, do that. I'm going to go back to my picture. I want to look at, remember, we are in this shaded region still. I'm going to take off some markings. So let's get that shaded region back in there. So we are still in the shaded region, but now we are asked to slice horizontally. So think of your horizontal slices. If you want, think of them as people laying sideways. That's kind of the way I think about them. Think of those little slices as people laying sideways, and the head always goes to the positive end. So if you're visualizing a person, it's going to be oriented as following. The head's going to be going to the right, the feet are on the left. So there's my little sideways. That's a little sideways stick person right there. That's a person like laying sideways, so you can visualize the head is on the right, the feet is on the left. And let's scroll and see if I can keep some of this on the page as we talk about the final stage here. So that picture we're looking at, the first thing we need to do is describe x. See if I can keep it, there we go, slightly on the page. I'm writing at the very, very bottom of the page, describing x. Remember, x is going to be bounded. And we want to think of the floor and ceiling example again, but we're sideways now. So you want to think this is the left wall in x equals format, and this is going to be the right wall in x equals format. So go back to that picture. I know it's a lot of scrolling. Back to that picture. Think about the leftmost wall. Who is everybody's feet touching if they're laying sideways? What is the equation in x equals of that wall? Well, that is the y-axis. That's x equals 0. So the left wall is going to be x equals 0. You can see I added that in below. Now the right wall is where we might have some issues. The right wall in x equals format. Go back to your picture and think about who is everybody's head touching. Well, everybody's head is touching this slanted line if they're laying sideways. The slanted line is found by the following formula. But we need it in x equals format. It's not in the right format, so you need to solve this for x equals. So solving that slanted line for x equals becomes x equals 3y. So remember, these two formulas describe the same thing, just from a different perspective. One's a y equals, one's x equals. But with horizontal slices, the rightmost wall is that slanted line, x equals 3y. So 3y is what goes there as your restriction. So we have restricted our x's, and now we're on the path to describe y. And this just means we're looking for the smallest y value in our shape and the largest y value in our shape. So go back to the shape and just identify who is the smallest y value, who is the largest y value. Back to the shape, zoom in, look on the axis here, and think about this shape. Who is the smallest y value and who is the largest y value? And we'll see that this, oops, I accidentally grabbed an eraser, try again. We'll see that the smallest y value is y equals 0, and the largest y value is that y equals 2. So let's go put that in our final answer, and then we'll summarize and be finished. So there we described x and we restricted y. If I just want to summarize and put all that together, I'll just rewrite it a little nicer down here. So this combination, this box combination of inequalities is how we would describe that region if it were sliced horizontally. Notice above, the set of inequalities from part A described the same region if you slice vertically. So do keep in mind, part A describes the same region as part B, just with a different slicing perspective. And when you take your vector calculus course and you get to double integrals and slicing regions, come back and rewatch this video so you can practice learning how to re-slice. Change your slicing to prepare yourself for the integration part. So keep this in mind. Now that you've practiced a little bit, make sure you revisit this when it's time for you to get into more complicated stuff in your calculus course. This summarizes all of the categories we covered, all of the main topics. Obviously, this video could go on and on and on, and I could just keep talking about more vector calculus topics, but hopefully this is enough to give you a little bit of a leg up on things you're going to be doing throughout your term or semester. In this document, though, you're also going to find just a little set of wrap-up and tips. I would say go through this, read through some tips, make sure your formula is right, a couple of quick reference formulas, some tips for Math 254, and then some reflections, some to think about. But maybe even more importantly, if you keep scrolling down, I put in a little post-test here. Just has a little quick multiple choice test on how to test yourself. Did you absorb some information from today? Go through and practice on your own. They're just kind of some of the more basic problems, not the more challenging ones. Practice on your own, and then at the end, you will find at the bottom of the screen down here at the very end, you do have your answers. Don't look at those right now, but you do have your answers listed for you so you can check your work. Thanks so much for joining me for this, and please make sure to request any other topics. If you find a topic you want me to get more heavily into, I'm happy to do that in a future video.